Stan Gibilisco here. I am going to back up a little bit in my book Teach Yourself Electricity and Electronics 6th edition to chapter 24, the chapter on electron tubes. And some of you might be surprised to find that I'm still discussing electron tubes 15, 16 years into the 21st century, but they're still around, particularly in high power transmitters. And if you want to know all about electronics, you're going to have to learn how these things work. But what I'm here to do right now is to explain the function of each individual component in a simple radio frequency triode vacuum tube amplifier circuit. Now, a triode vacuum tube, this is the symbol. This electrode is called the cathode, and it emits electrons, free electrons, which travel through essentially a vacuum, not uh, atoms with electrons missing or extra electrons added, as in semiconductor devices, but an actual vacuum through which electrons travel. This cathode is heated by a wire filament similar to the filament you'll find in a light bulb, which heats it up to a temperature that encourages it to throw off any electrons that it might have on it. It's a metal electrode. The actual construction of the vacuum tube differs considerably from the schematic symbol, but I'm showing here the function of the individual components. This is called the control grid. Because it has three elements, this is called a triode vacuum tube. This is called the anode or the plate, and it receives a positive high voltage, can range on the order of plus 45 or 50 volts to plus in excess of 3 or 4 kilovolts DC. What happens here with this amplifier, and we don't need to worry about whether it's a power amplifier or not, but what we do need to concern ourselves with is what these various different components and elements of the tubes actually do. The closest analogy I can draw for you for a vacuum tube to a solid state semiconductor device is to an N-channel field effect transistor. The grid corresponding to the gate, the cathode corresponding to the source, and the anode or plate corresponding to the drain. The input signal comes in, radio frequency signal. This is a radio frequency amplifier. The blocking capacitor keeps the input circuit from disrupting the performance of the vacuum tube, and also keeps the control grid of the vacuum tube from being shorted out to ground, keeps the tube from disrupting the performance of whatever happens to be at the input, probably a radio frequency oscillator or a low-level radio frequency amplifier. This resistor right here provides a certain negative voltage on the control grid. This resistor here allows for a certain negative voltage to exist on the cathode. Negative because this power supply voltage is positive. You will never find the anode of a vacuum tube negatively charged except in certain strange situations with rectifier circuits. This is not a rectifier. This is a Class A amplifier circuit for which the signal flows for the entire cycle through the vacuum tube. Electrons come off of the cathode, pass through this wire screen or mesh, the control grid, and depending upon the instantaneous negative voltage on this control grid with respect to the voltage on the cathode, you will get more or less electron flow arriving at the plate. And by electron flow, I literally mean electrons flowing through a vacuum, free electrons. When the electron flow is higher, you get more current. When the electron flow is lower, you get less current. And as this signal alternates, passing through this blocking capacitor, and changes the voltage on this control grid to more negative, then less negative, then more negative, then less negative, but always negative with respect to the cathode, you will get DC modulated by the audio frequency or by the radio frequency signal. Well, it could be audio frequency just as well, but because this is an open air core transformer, you can be almost certain it's a radio frequency amplifier. You tap this coil at a point which provides a matched impedance between the output of the tube, which is usually quite a high impedance, and the input of the next stage, probably another amplifier or possibly an antenna, which will have a low impedance. That's why the tap is somewhere in the middle of the coil, or maybe even closer to the positive voltage. I'm assuming that the filter capacitors in the power supply will provide signal ground for this electrode here, but you could connect a capacitor between here and ground for additional insurance to be sure that this is in fact at radio frequency ground. So what you get is DC modulated by an RF signal, the blocking capacitor again preventing the output circuit's input from getting shorted out by the coil and preventing any direct current interaction between the two circuits while allowing RF to pass. So these are blocking capacitors, and these resistors provide the proper voltage bias on the vacuum tube so as to allow fluctuating direct current to come out of this electrode, flow through the coil, get tapped off, and you get an RF signal here that is louder than the RF signal here. So you can think of this as an analog, a high voltage analog to an N-channel field effect transistor circuit, even though the internal construction of an N-channel field effect transistor differs radically from the internal construction of a vacuum tube. If you haven't had experience with vacuum tubes, it's never too early or too late to get it, because if you are serious about radio frequency power amplifiers in particular, you are going to want to know how vacuum tubes work, how to operate them, and how they are constructed internally. And you'll also want to be aware of the fact that the high voltage commonly encountered in the power supply of a vacuum tube is deadly. 600 volts is, if you should happen to touch that negative voltage point, a sufficient amount of current can flow through your chest cavity to kill you, to stop your heart from beating. So you don't mess around with these circuits. These are not like the little toys that you find, toys by comparison, in terms of the lack of danger they present. These are potentially dangerous circuits, and you need to treat them with the appropriate respect. But those are the functions of the components of a simple triode radio frequency broad-banded vacuum tube amplifier. If you place a capacitor, a variable capacitor, in parallel with this coil, you can get resonance at the frequency that you desire, but you also run the risk of the circuit breaking into oscillation. So I hope that outlines for you basically what the functions of the individual components in a simple electron tube or vacuum tube triode amplifier do. Triode again, 3 elements. Triode means 3 elements: cathode, control grid, and anode or plate. Stan Gibilisco signing off. You'll find this information in my book, Teach Yourself Electricity and Electronics, edition number 6 on page 406. This is figure 24-4. You'll also find it in other editions of Teach Yourself Electricity and Electronics. Until next time, so long.